Well, I kind of messed this one up, haven't I? Right, looks like we've got 4 people here, so this is the worst thing. Here we go. Right, I admit that was a bit of a mess. Sorry, I'll get better next time. Um, how are we all? Who is here? Tell me who is here. No one's here. Brilliant. Talking to myself again. It says there's 3 people watching. Well, there was 4 before I played that intro, which means that one person didn't like it, I guess. If you're here in the chat, just I see Owen and Amy are here. That is that's grand. Right. Good. Let's hold on a second. I need to sort my life out here. YouTube changed the well. There's something going on with YouTube, basically. There's my excuse. Right. Okay, anyway. So what we're going to have a look at today, we're going to have a look at cryptographic hashing. So by the end of this lesson, you will be able to explain what the term hashing means. You probably already know what hashing means, and we've done some little exercises about hashing. Investigate a number of simple hashing algorithms. I call them hashing algorithms. Technically, they're not hashing algorithms, but we'll have a look at some real hashing algorithms and how you can use Python to do that. And then there's that website that I had you set up. Investigate, and maybe we'll go through that with a little bit more detail, so you can see exactly what's going on. And I hope to explain sort of what's going on a little bit better there. We'll see how it goes. All right. So first of all, some stuff for your notes. You need to know what a hashing algorithm is, right? A hashing algorithm is something that takes data of arbitrary size. Do you know what arbitrary means? Just a Y or an N in that chat down there. Do you know what arbitrary means? Any? Is that right? Okay. I mean, you know what arbitrary means. It means that there's no set size. If we're talking about an arbitrary size, there's no set size. If we're talking about arbitrary laws, we're talking about laws that are made up on the spot and things like that. Okay, so it takes data of arbitrary size and maps it onto data of fixed size. They are used in lookup tables. In Python's dictionary function, I believe that the data is stored using what's called a hash table. You will find that most programming languages have something called a hash table, which is used to tabulate data. There's copious amounts of information on the internet about hash tables. You can have a look at that at your leisure. Okay, that's one of the places where hashes are used. They are also used to make the storage of passwords more secure, right? So specifically this lesson we're going to have a look at cryptographic hash functions. So remember, just in general, a hash function is something that takes a data of arbitrary size and maps it onto data of fixed size. Whereas a cryptographic hash function is a little bit more sort of finely tuned for use in system security and cryptography. So, a mythical perfect hash function does all of the following things. Okay, it always produces the same hash from the same message. So if I take the password 123456, which is one of the most frequently used passwords and is a terrible password, but if I take that password and run it through the hash algorithm once, I can take that password again at some later date in the future, 123456, when I run that through the hash function, I will get exactly the same hash on the way out. Also, we want our hash functions to be fast. We don't want to spend ages waiting for the hash to be computed because obviously time is money and all that. So a perfect hash function is going to quickly compute the hash. A perfect hash function should also be one way. Okay? What I mean by that is you should not be able to get back to the original thing starting from the hash. Okay? Why do you think it's important to only have one-way hash functions when we're using them to store passwords? Expand on that. Safer in what way? You're right. Easily find out the sensitive info. Yeah, technically correct. Yeah, I mean what you've just said there, the thing you're trying to protect. I mean, what's the point in taking a password and mashing it up into a hash if someone can just take that hash and reverse it to get the password? It completely defeats the whole point of the exercise, right? Some other things as well, other features which a good hash function needs to have, which you might not have considered. If you make a small change in the message you're encoding, you should get a huge change in the hash. Okay, so you shouldn't be able to tell that one password is close to another password by looking at the hash. If I have the password password, PASSWORD, that's how you spell it, and it hashes to one value, let's say, I don't know, x3987. If I put password 1, that should not map to any hash which is similar. You know, they need to be totally dissimilar, so you can't gain any clues as to what was changed. Because obviously, if you get to the point where, okay, I know the hash for this word, if the hashes are fairly similar to each other, then once you know the hash for one word, you can use that to sort of work out subsequent words, etc., etc. Does that make sense to everyone? And obviously, you don't want more than one message to map to the same hash, because then, you know, someone could have a different password or could enter a different password, and when it maps to the same hash, we check the hash there, and you know, they let you. You've got to have each word has a unique hash. That's the way it has to be. Okay. Now, to anticipate, I'm going to show you a diagram on the next slide, but just to anticipate any questions, when we store passwords, we don't actually ever store the passwords. We store the hashed version of the password. So the idea is, we store the hash. That's what's, you know, if you crack into the server, you get a big list of hashed passwords, which are probably fairly useless. And when a user types in their password, we run it through the hash function and we compare the hashes. We don't actually ever compare the password to anything else. We hash that password and then compare the hashes. Yes, except at school. Let's not talk about that. Okay, so let's have a look then at this little diagram, which I robbed from Wikipedia. I think I robbed this from Wikipedia. So we've got some input. That's the blue stuff on this side. This is all input. Wait, let me turn on my funky laser pointer. There we go. We've got some input on this side. This is the string or the password or whatever it is, the data which is being hashed. We run it through our cryptographic hash function. Okay, and what we get out of here, these are the hashes. They are commonly known as digests. Okay, this is the hash digest for this input. You can see all of the digests are exactly the same size. Okay, we've got 40 characters. 40 characters. Looks like hexadecimal. I don't know. I think it's hexadecimal. I don't know what hashing algorithm this is. Probably MD5 maybe. But like I said, I robbed it from Wikipedia. So even though Fox only has 3 letters, we still get these 40 characters out. Yeah, even though the red fox jumps over the blue dog is way longer than that, it's still the same, right? And you'll notice on this one here, the red fox jumps the blue dog. We've only changed a single letter in here, but look at the hash. It's totally different, okay? Tiny changes make massive changes in the hash. Tiny changes to the input, massive change to the hash. That is super, super important. Okay, because the fewer clues we can give to someone, the more difficult it will be for them to crack the hash. Does that make sense? Yes. Cool. So I don't really need to go over this in much more detail, right? We get the idea. We're taking some input, we're running it through a function, we're getting a digest out the other side, and said digest is going to be the same length regardless of our input. And all of these digests are unique. They're totally different to all of the others. Doesn't matter what input you put. Only this input will give this output. Only this input will give this output. Okay. You may come across the term hash collision. Okay, a hash collision is when you've got 2 different inputs and they map to the same hash. That's what's called a hash collision. So if you're doing some research and it says, oh, the perfect cryptographic function will not have any hash collisions or will not have any collisions. Not the same as a network collision. Okay, it's to do with the hashes. All right. Are we ready? Are we ready to move on to an example here? I've got a couple of examples, and then I mean, I said before this is going to be like fairly light on the me bit and a little bit more heavy on the you bit, but we can go through some what's it called? Programming examples. Is that all good? Cool. So here's a really simple hash. It's debatable as to whether or not it's even a hash, because if we're just dealing with denary numbers here, then obviously we're going to map to different lengths, but we could potentially pad it out with numbers or whatever. Okay, so this is the world's simplest hash. It's terrible, it's not good, do not use this. We start off with a total of 0. We have our alphabet here, A, B, C, D, F, G, H, I, J, K, L, M, N, P, Q, R, S, T, U, V, W, X, Y, Z. Okay, and for each letter in your message, all you do is look up the position of that letter in the alphabet and add that position to the total, and then output the total. Okay, so for example, if I had the word password, you know what? I'm going to do an easier one because I don't want to have to count along here. If I'd actually had any sense, I would have planned this out a little bit better. Let's say our password is ABC. Okay, A is at position 0. B is at position 1, C is at position 2, 0 plus 1 plus 2 equals 3. So the word ABC hashes to the value 3. Okay? Like I said, to anyone who is in any way affiliated with anything related to computer security, please don't roll your eyes if you're watching this on a rerun or you stumble across it. You know, I'm using a very simple example to explain to my students. Okay, and if you got a problem with it, fight me. Yeah, I went there. Now, what's the problem with doing it that way? Okay, if I have this password ABC and it hashes to the value 3, what is the problem? And see if you can use the correct terminology in your answer to that problem. Nobody knows. Nobody knows. Does anyone know? Anyone? You guys still alive? What? I'm confused. 6. What does that mean? Let's say, right, okay. Let me go back and rephrase this. Let's say, for instance, I have a password which is ABC. Okay? What does the password ABC hash to using this this method? The password ABC, assuming that A is 0, B is 1, and C is 2. What is the hash to ABC? Correct. The hash for ABC is 3. Okay, boom, right, Jermaine in with the answer there. That's what I was leading up to. You get a hash collision if you have another password. For instance, ABC, as Owen quite rightly pointed out, hashes to 3. But D on its own also hashes to 3. Okay, so there's a collision there. In fact, you're going to get tons of different collisions because this is the crappiest hash in the universe. Like I said, it's debatable as to whether or not it's even considered a hash. Okay, but it's useful as an explanation, as a preparatory tool to prepare you for the next step. How many of you like prime numbers? Just a yes or no down in the chat there. Prime numbers, are they good? Are they bad? What do we think? No, says Amy. You'll be pleased to know you don't have to actually calculate any prime numbers. But there is a reason, right? I mean, I showed you that this is kind of weird because we've already sort of done the exercises that lead on from this this theory lesson. But prime numbers are a good thing when we're talking about cryptographic hashing, and there is a reason for that. What is so good about prime numbers? Did you know this? I don't know whether you knew this. Every single number in existence, integer number, I should say, every single integer number can be expressed as a product of prime numbers. Okay, as an example, 255 is 3 times 5 times 17. Okay, you can do that sum. You will get 255, right? There is no other combination of prime numbers that will get you 255. Okay, every single number can be expressed as a product of prime numbers, and that set of prime factors is unique to that number. Okay, see where I'm going with this? Does that make sense? Yes. Good. Okay. I'm going to assume that you guys know how to do prime factorization. Is that a reasonable assumption? Yeah? Yeah, good. You could even write a program that does prime factorization. I mean, it's fairly straightforward. You'd have to use the modulus function to get it running. Tommy, there's a challenge for you. Write a program that will take any number and do a prime factorization on it. Okay, next up then. Let's go to the next slide. So here is an example of another hash, if you like. I mean, again, it's debatable whether or not you can call this a hash because it doesn't necessarily produce a fixed length digest. Okay, but take my word for it, these are the first 26 prime numbers. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97, and 101. Okay? So, if we map each of those to a letter, we end up with A equals 2, B equals 3, C equals 5, D equals 7, and so on and so forth, right? So this time, what we can do is, instead of just adding numbers together, we find out what the prime that represents each letter is, and we multiply that onto our current running total. Now you've got to start your total off at 1, otherwise, if you start off at 0, then you're going to end up with 0 every single time. Okay, so we start off with 1. I mean, total, maybe that's not the greatest word. Product would probably be a better word here. Okay, and so for each letter in the message, what we're doing is we're multiplying total by whatever the equivalent prime number is here. Hopefully this pseudocode is understandable to you. This is not Python, this is pseudocode. Okay, well, I'm saying prime's letter index. What I mean to say there is whichever index the letter is in the alphabet, look up the corresponding index in our list of primes and then multiply that by the total. Okay, so for instance, if we were doing our ABC password again, we would have A is 2, okay, so we do 1 times 2, which is 2. B is 3, so now we do 2 times 3, which is 6. And C is 5, so we do 6 times 5, which is 30. So ABC hashes to 30. Does that make sense? Does that make sense? Yes. I never asked for this. Cool. Okay, so obviously in this scenario, ABC maps to 30, D maps to 7, so that issue that we had before regarding collisions is no big deal. And as I have just said, every single number maps to a unique combination of primes, which means if you take a bunch of prime numbers, you multiply them together, you're going to have a bunch of unique output numbers. Does this remove any hash collisions? Just yes or no. Do you think this removes all hash collisions? No. No, says Jermaine. No, says Owen. No, says Amy. You are all correct. Yes, and Jermaine has anticipated my next question, which was where do the collisions come in? Although this will build up a unique set of letters, ABC is the same as CBA, and so on and so forth. Okay, so it doesn't matter what order you get those letters in. Okay, which means that you could find out what the hash is and still not know the password, but still get in as long as you got the numbers correct. Okay. So I'll tell you what. Before we go on to this next bit, shall we just open up that website? I'm going to post a thing in here. www.666.co.uk /hash hack. Oh god, yeah, that should still take you there. And let's just have a look at the thing. Did I add the thing? I don't know if I added the thing. No, bear with me one sec. I just need to add my little doobry. I'm going to have to do some on-the-fly editing here, guys. Bear with. There we go. Okay, and like a boss. Here we go. Right, so let's just bring this to the foreground here. So this was the website that I gave you guys, and the first couple of levels go through what I've just gone through. Okay, if you press Control U, you can view the source code. Here is the source code. It doesn't matter if you understand JavaScript or not, right? If you have a look in here. This is the key line here. We're saying if password equals password, window.location.href equals level2.html. So we've got two ways that we can get through. We can either type in the password, which is password, or we can just point the address to level2.html. Okay, so I'm just going to type in the password, and we are now at level 2. Okay, here's level 2. Once again, if we view our source code, it's a lot messier now. Okay, ignore all of this stuff. This is the bit that we're looking for here. We've got a function called hash. This is the function. This is the same function that I talked about earlier on when we were just adding the values of each letter in the alphabet. Okay, this is written in JavaScript, but you could easily implement something very similar in Python without really changing an awful lot of the syntax here. But the key point is that we're saying if hash password dot to uppercase equals 40, then we're going to move to the next. We're going to move to the next level. Okay, so based on that, and knowing that the hash is that really simple one where we're just adding the values of the letters in the alphabet together, what is the easiest way of getting through to the next level? What password should I put in? Someone tell me. You can put 40 B's in there. Yeah, that's something that you could do. I mean, there's tons of different ways. I can't actually remember. There was originally a password. I can't actually remember what that password was. But the fact that there's so many collisions on this means that, yeah, like you said, KKKK, if we log in there, it takes us to the next level because, we're just adding those values together. K is equal to 10, so 4Ks is equal to 40, right? Now, this time around, we are using we're using prime numbers. Okay, so you can see here, if I just go into this hash function, we've got our alphabet, A, B, C, D, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, U, V, W, X, Y, Z, and then we've got the list of prime numbers. They map directly to each of the letters as before. Okay, so it says here, if hash password dot to uppercase equals 2552308, then we go in. So what we need to do is do prime factorization on that number. Okay, divide by 2. Does it evenly divide by 2? If it does, then boom, there's our first one. It's a 2. Now, are you guys aware of Wolfram Alpha? You guys aware of Wolfram Alpha? Do you know this site? Yeah? Okay, if you've used this site before, you'll know how easy it is to just take a number like this and go prime factors of this number. Boom, there we go. Let's find out what those prime factors are. We've got 2 squared, which means there's 2 2's in there. There's an 11, there's a 19, there's a 43, and there's a 71, right? Based on that, right, can you guys tell me what the password is to get through to the next stage? And while you're working on that, I'll go and make some coffee. Yes, I know you're looking forward to the sound of the coffee grinder. Well, you're going to get it. Don't worry. I'll be back in about 5 minutes. So use that. Find out what the password is to the next stage. Okay, and as a bonus, if you can work out what the original password was, because remember, these factors, they're not necessarily in the order that I intended them to be in. See if you can work out what the original password was as a bonus. All right, I'll be back in a sec. Cool. Do we have an answer? WhatsApp is not the password. Anyone want to tell me what the password is? What do we got? What's the password? Can't let you in without the password. I mean, hentar will work. Ain't will also work. Okay. Yeah, in any order. I apologise for talking with my mouth full. The actual password was Athena. Okay, you'll notice that is the same as the letters that you had, but obviously with this it bears no regard to order. Okay, so in order to make sure, haha, see what I did there? That was unintentional. In order to actually make it recognise that CAT, TAC, and ACT are all different words, there's something else that we do here. And in my example, just view the source code again. In my example, what I do is I add on the previous prime number. I add on the previous number onto our running total, and then arbitrarily mod it with this number here, the 3989, because that was just a number that came off the top of my head. Okay, now I'm not going to dwell too long on this. Okay, this is just a silly function that I came up with to make it more difficult for you to crack and to give you an idea at writing a brute force algorithm. We will come back to that though, and that whole idea of taking the previous number and adding it on after you've worked out what the next prime total is going to be, that ensures that the order is preserved. That makes it way more secure. Okay, now I designed this so that you can write a brute force cracker to try and get through it. I know that Owen was successful in that. The rest of you do not know. If you got it working, then by all means send me the code on Discord. We will come back to that. Okay, but for now I want to get back to this here. But before I move on, does any of this stuff sort of like fill you with dread, or is there bits that are still confusing to you, or are we sort of like, are we all good? I mean, if you don't understand how to write the brute force algorithm, that's not necessarily the end of the world, as long as you understand why the need is there. Does that make sense? Just what I'm saying is, before I move on to the next bit, have any of you got any questions? Here's your overview, Alex. We've gone over cryptographic hashing. I suggest going back and rewatch the video because I ain't going to recap that. So we all good? Yeah? Yes, no, good, yeah, yeah. Anyone got any questions? We all seem all right. Oreos, by the way, quality biscuit. I mean, they're not minty, but they're a good biscuit. You can get them pretty much everywhere as well. It's not like there's only one place where you can get them. I'm not sponsored by Oreos, by the way. In fact, Aldi do like a rip-off of Oreos, and they're way cheaper, and they're just as good. So, wicked. There is a potential problem. Let's assume we have a perfect cryptographic hashing algorithm. Right now, as I said, the perfect the perfect cryptographic hashing algorithm will always hash a string to the same digest, yeah? And different strings will hash to different digests. Okay? So there's a problem here. Let's say Mr. Nasty Cracksaw gets hold of a list of all of the digests that are stored on your server. Because you're sensible, right? You don't store your passwords in plain text because you think, if I store my passwords in plain text, someone's going to find all of those passwords. I don't want to do that. You know, I'm going to store a hashed version of them so that if I get hacked, all they'll get is the hashes. And yeah, I mean that's still potentially bad, but there is still this problem though, right? You get hold of a list of all of the digests, you can potentially try cracking some passwords. Question for you is this: what happens is, no, that should say if. I apologize. What happens if multiple users have used the same password? What are you going to see in your list of hashes if multiple users have used the same password? Repeated hashes. Why are repeated hashes bad? Well, I mean, what's the potential risk here? Yes, well anticipated, Alex. What's the potential risk? You're entirely correct that you will have repeated hashes. Now that's not a problem for the day-to-day running of the website or the system that you're using, but why does that potentially present a weakness? Boom, there's the answer. Okay, if you've got 20 hashes which are exactly the same, you know that every single person that has that hash has the same password, so you crack it once and you've got all of their passwords. Okay, now there is a way around it. Okay, there is a way that we can fix this. We can fix it so that even if different users have the same password, they actually have them stored as a different hash. And you're probably thinking, yeah, but sir, you said that the same string always produces the same hash. So, like, if that's the case, then how are we going to have different hashes for the same password? I know that some of you are probably thinking that. But this is the answer. Okay? We use something called salt. Okay, it's not salt that you put on your chips. Okay, it's a string of random characters, and you add those random characters to the password before it's run through the hashing algorithm. Okay, I was supposed to get a picture from Wikipedia and paste it into the document, but I totally forgot. So if you just bear with me 1 second. Disambiguation. Here we go. There's a reasonably good example here. on this Wikipedia page, which apparently does not fit in the little window that I've got here. Boom. No, that's the that's not it, is it? That's the chat. Oh, come on, Smith. What are you doing, for God's sake? Okay. Right, so have a look at this. We've got user 1 has the password 123, which is a crap password. User 2 has the password 123, which is also a crap password. They are also the same password. If we did not use salt, then we would not be able to... we would end up with 2 identical hashes stored in the system. Okay, so what happens is when user 1 creates their password, random salt is generated and added onto the password. So this whole lot here is what gets hashed, right? User 2, they have the same password, but they have a different randomly generated salt here, and so that is added to the password, and they get an entirely different hash. Okay? And then when it's stored, you store the hash values and you store the salt. Now that doesn't make it perfect, okay? Because the salt is random though, it means that if you discover one password, even if people have used identical passwords, you won't be able to tell who's used that same password because you've got that random salt added, okay? So it's an extra level of protection there. What's this? If you use the same salt, then the same problem applies. How do you? So you don't ever use the same salt. I mean, it's randomly generated. Every single password has a different salt. Okay, and then you store the salt with the hashed value. Okay. Now, obviously, if someone gets hold of the hashed value and the salt, then in theory they can just add that salt on when they're doing their brute force. Okay, but it still makes the passwords less susceptible to dictionary crackers. So there you go. Okay, how do you generate the salt without it being reversible? I'm not sure what you mean by that. Hash algorithms are, if they're decent, if they're worth their salt, see what I did there, they are irreversible. Let's just get rid of that. Okay, so the hashed password and the salt are stored, and as every salt is random, ensures that if one hash is discovered, the identical passwords remain safe. Okay, so little bit of extra security there. That's actually a bit more detail than you actually need to know for A level. Okay, but hopefully that will give you some ideas when you're doing your research. If you run into concepts like salted hashes and stuff like that, you will understand what that means. Salts are generated when the password is created. Okay. Anyone got any questions about cryptographic hashing or salts? No? Cool. Right. Few questions for you then. And you can put these answers down in the chat there. What is hashing? What is cryptographic hashing? What separates cryptographic hashing from any common or garden hashing algorithm? Why is cryptographic hashing important? And what are the things that I mentioned that make a quote-unquote perfect hashing algorithm? Okay, answer those questions. You don't have to answer in order. Maybe choose one and answer it so that we get a variety of different answers down there. Okay, I will await your answers. And then, if anyone wants any help with that brute force program, then maybe I'll go over a few bits and bobs there. No, I've not gone over how the hashing algorithms actually work because they tend to be incredibly complex, and I mean, I gave some examples of some basic hash algorithms, but I've covered all the stuff that needs covering. So answer them questions in it. Perfect hash always produces the same hash from the same message. It needs to be fast. It needs to be one way. A small change in the message produces a huge change in the hash. It does not map to more than one message on the same hash. That is good. Mapping data of arbitrary length to one of fixed length is what a hash algorithm is. Excellent. Takes data of arbitrary size, maps it to data of fixed size. Okay, so so we've said what makes a perfect hashing algorithm. We've said what hashing is. So what's the difference between normal hashing and cryptographic hashing, and why is it important? Well, any decent hash is one way, but yeah, a cryptographic hash has to be one way by definition. What else we got down here? Yes. So why is cryptographic hashing important? Yeah, I mean, generally speaking, I mean, you can have cryptographic hashing algorithms without salt, although these days there's stuff that you don't need to know about for A level, such as rainbow tables. Salt helps to prevent against rainbow table attacks. So if you go to Wikipedia, you can read all about rainbow tables if you want. Yeah, in terms of quantum computing, who knows? Who knows what's going to happen? It's going to be an interesting time, but I don't think we really need to worry about that right now. Did anyone, just out of interest, did anyone want me to go over the brute force algorithm for cracking stage 4 of that hash hack website? Did you want me to go over that at all, or are we good? Amy says yes. Okay, right. Well, I'll tell you what. I will go over in the time that remains. I mean, we've been on for about an hour. Well, we've been on for 55 minutes, so it might take me a little while to explain what's going on. But I'll tell you what I will do. Rather than showing you exactly how everything works, I will show you how to convert the JavaScript hash function to Python, yeah, and then I will show you how to do the IterTools product thing, and then I will let you have a go at getting it working. Yeah, I mean, stick around if you want to, or go. I don't mind. Okay. So it's remember, this is your. There's no point you sticking around if you already know all of this stuff. But there we go. Okay, are we good? Cool. Hey, what's this? PyCharm. That's right. Let's increase the size of the font there. Is that font size big enough for you? Can you see? Can you see that font all right? Mini tinks. Not really. Okay. Let's see if I can increase that a bit more than potentially difficult without having it go off the. I mean, okay. Is that better? I mean, it sort of scrolls off the screen a bit. I'll tell you what I'll do is I will put this down on multiple lines so that we can still see everything there. Does that make sense? Is that good? Is that better? Yep, cool. Right. So what I have done here is I've started off, I've got my alphabet, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, U, V, W, X, Y, Z, and I've got my list of primes. Okay, and if we just have a look at the source code for this website, you can see here I've got my alphabet and I've got my list of primes. Right, I'll tell you what I'm going to do is I am going to copy and paste the JavaScript function into Python. Now obviously that's going to come up with a whole bunch of horrible errors like this, but we'll go through it line by line and we'll do a quick port from JavaScript to Python. Okay, so got here function hash string. Well, we can rewrite that in Python. The equivalent for Python is def. We're going to define the function. We're going to call it hash, and it takes a single argument string. Okay, so there's that first bit. Boom. Okay, that is equivalent to this little line here. So I can now get rid of that line there. We've got alphabet equals blah blah blah. We've got primes equals blah 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 blah. Okay, I could probably even get rid of that stuff at the top there. You can't see my Python. Of course you can't see my Python because I'm a bloody idiot. There we go. That's it better, right? So I've if I just go back using the power of Control Z, that's where we were. Well, I've replaced that function hash string with replacing this with def hash string, like that. Okay, that makes sense, right? That line in Python is equivalent to this line in JavaScript. Okay, so now I am going to delete that line here. I've got my alphabet and I've got my primes. Some terrible kerning on this font, but whatever. Just going to make sure that you can see all of this all at one time. Get rid of that semicolon on the end. Get rid of that semicolon on the end here. We're almost, I mean, this almost looks like Python, right? Var total equals 1. Well, in Python we don't have to specify if something is a variable or not. We just give it a name. Okay, so we're going to start off with total equals 1. Yeah. And we have this variable called prev, which is the value we're going to hold for the previous variable. Okay. Still with me? Feel free to shout out if none of this is sinking in. You know what? I'm just going to get rid of that lot there for science. I'll get rid of all of this. Fine. There we go. Cool. So now we've got a for loop. Now the way that for loops work in JavaScript, it's kind of different to the way that they work in Python. But what we're saying is we're starting at 0 and we're going all the way through the length of our string and we're adding 1 on each time. We can convert that to Pythonese if you like. by doing something like this. For I in, well, what do we use there? We've used x there, so let's do for x in range len, because len tells us the length of the string. Okay, that there does the same thing as this line here. Okay, we've got string.length, that's the same as len string, and we're saying start off at 0 and go all the way up, blah 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 blah. So now I can get rid of that line there. We've got this other variable called position. Now let's have a look. In JavaScript, this is bothering me now. In JavaScript, we have this index of. Well, in Python, we don't use index of. We just use the square brackets, or we use the index command. I'm just trying to work out what this line of code actually does. Position equals alphabet.index of string.char at x. Right, string.char at x is equivalent to saying string x, like that in Python. Okay, position equals alphabet.index string x. What that does is it will find out what our current letter is. Okay, so remember we're starting off at 0. String 0 is going to be the first letter in the string. String 1 is going to be the next letter. String 2 is going to be the next letter. And it finds out what the index of that is in the alphabet. Okay, so if our letter was A, it would return 0. If our letter was B, it would return 1, and so on and so forth. Okay, that is our position. So now we're going to multiply total by prime's position, and we're going to add on our previous value. That line is virtually identical to the line that it is in Python. Okay? So prime's position, what that means is go to whatever position in our list of primes that we've got out of here, okay, and then multiply that by total and add on the previous value. Okay, and then our previous value becomes the total mod 3989. Okay, we don't need that. Once we've done that, we will have our total at the end. We can return the total. Okay, and there, that is the JavaScript function. That's the JavaScript function converted to Python. Okay, and yes, you can adjust this. You can just do for letter in string, for instance. What I did was just try and make it look as close to the JavaScript original as possible. Right, and we can test it out. Right, if we did print hash, give me a string, hello. Okay, if we run that code now, hopefully we get some output. Control Shift F10. We get an error. What error do we get there? Substring not found. Oh, of course, because we need to make sure it's block capitals. There we go. And our output from that, the hashed version of hello, is going to be that ridiculously large number. Okay? So, in order to brute force this stage of the hash hack site, let's just go back to the old hash hack site. Okay, let's look at the source code. this here is the number that we are looking for. Okay, that is the number that we're trying to work out. I'm going to paste that in here. I'm going to call it target hash. Okay, it's a large number. That's the number that we're going for, right? So what we need to do is we need to have a loop that goes through every single possible combination of letters. It's only uppercase alphabetical letters. We're going through every single combination of those until the hash that we get is that. Okay? Now the function that you will need to use in order to get this sort of working to an extent is the itertools function. Okay, I'm going to import the itertools module up here. Import itertools. Now, itertools has a function within it called product. Okay, if I say print itertools dot product let's see if we can see all the different combinations of ABC, all the 3-letter combinations of ABC. Repeat equals 3, like that, and we're going to print. Going to convert that to a list before we print it out. Okay. Just comment those out. Okay, if I run this now, okay, that didn't work the way that I expected it to. Might have to convert it to a list the old-fashioned way. Is that going to work? Yay. Okay, you can see here in my output. How do I get rid of this bit? You can see here in my output, I have specified these are the potential values that we can use, right? And this is how many things we need to check in there. Okay, so we've got AAA, AAB, AAC, ABA, ABB, ABC, ACA, ACB, ACC, and so on and so forth. Okay? Which means if we replace this with the alphabet, LM, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, right? We can then go through each of the items in, because this generates a list, right? So we could do something like this. For, let's call it combo. For combo in itertools.product, blah, 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 blah. Print, dot join, combo. Now what this is going to do is it's going to go through all of the possible 3-letter combinations of any of the letters in the alphabet. Okay, it's going to join them together into a string. Right, so when I run that, you can see there's all of those different combinations. Now obviously we don't just want to print this stuff out. We want to run it through the hash function. Yeah? Why that syntax? That's just how, right? So the way that this works is this is a string, yeah, and what dot join does is it takes an iterable. In this case, it's the different combinations, and it will join all of the individual items of that iterable together using whatever's in the middle here as the glue, if you like. So I could put a hyphen in between everything like that. When I run that, you can see that it's printed that stuff out like that. Okay. Would F combo work too? I don't know, let's try it. No, doesn't work the same way. Okay. Okay. Now, obviously, we're not going to print that out. What we want to do is we want to hash it. We want to run it through the hash algorithm, right? So let's do this instead. Okay. This time we are joining those combinations together. We are sending them through the hash function, and then we will get a hash value out. Yeah, we want to compare that hash value to our target hash here. All right, if I was to print, what's it called, new hash. If I print that new hash out, we can see what that actually looks like. He says, okay, here's all the different hashes for all of those different combinations. Now you can see that none of those hashes are even remotely close to this hash, which suggests that maybe it's a longer word. So here's what you need to do, and this is the bit that I'm not going to go through directly. I want you to have a crack at this. Okay, you've got your hash function, right? You've got this function called itertools.product, right? At the moment, we're fixing it to a specific length. Yeah. What you need to do is you need to go through all of the one-letter combinations and find out the hash, and then you need to compare the hash to the target hash, right? You need to do something like if what's it called? New hash equals, and then here's our target hash here. Because if we got the hash value and it equals that, we know that the password's correct, right? We're going to then print we're going to do that. Okay? We're finding that combination. Yeah? We're getting the hash. We're comparing the hash to our target hash, and if it's the same, we know that that's the correct password, so then we're going to print out that password. Okay? Now, the password is not 3 letters long. Who knows how many letters long it is? So what you need to do is write a while loop, or maybe a for loop, which increases that. So instead of just having that number hard-coded in there, you need to come up with a variable which is going to increase. So if the number is, if repeat is set to 1 the first time through, you know, if you don't get an output there, you need to then increase to 2. If you don't get an output there, you need to increase to 3. If you don't get an output there, you need to increase to 4. Bearing in mind that every time you increase that number, it increases the time it's going to take to crack by a long, long margin. Just for reference, my program to crack this took about 4 hours. Okay? So it's not, you know, it's not the most secure thing in the world, but it's not designed to be. Okay. However, that is about all the help I'm willing to give you here. Okay. I've led you by the hand up to this point. Okay. Do you feel confident enough to complete that program and see if you can get in? Okay, give it your best shot. Feel free to ask me for help on Discord, send me some code. If your code's not working and you don't know why, send me that. If your code's kind of working, or you think it's working but you don't want to sit there and wait 4 hours to find out whether it's working or not, then by all means send me the code that you've got. Okay, if you've got any questions at all, let me know. All right, that, my friends, is about the end. Are we good? Is that good? So thumbs up, thumbs down. Still got 6 people watching for some reason. That's kind of cool. I apologise for the sort of haphazard nature of this lesson. I sort of pulled it together fairly rapidly, and we'd already done a lot of the stuff in the lesson already. But I hope you've got a firmer understanding now of cryptographic hashing, why it's useful, and potentially a better understanding of brute force cracking methods and why they end up taking a long time. Okay. Wow, look at that. 1 hour 17 minutes. That's a reasonably long one. That's it. Remember as well, if you run into any problems, consult your duck. They will. That's what I do. That's why he sits here by my desk. Okay, so let me know how you get on with that, and I shall see you all. Well, I'll have a tighter timetable of when these live streams are going to take place up by the weekend, and that's that. That's the end. It's over. This whole dream. It's not what I wanted. It's what you wanted. I never wanted it. I just didn't have the guts to tell you. That's not my words. Those are the words of a character in a movie I saw once. The character's name was Keith, and the movie was Some Kind of Beautiful, which is a great film. You should watch it. That's it. The end. Goodbye.